Welcome, and thank you everybody for joining us for today's C2 Smart webinar. I am Lizzie, the Research Project Manager at C2 Smart, which is a US DOT Tier 1 University Transportation Research Center. C2 Smart leverages recent advances in big data and technology to solve today's urban mobility challenges. Today's webinar is New York Statewide Behavioral Equity Impact Decision Support Tool with Replica. Our presenter is Yaron Wen, who is a fourth-year PhD student in Transportation Planning and Engineering program at NYU Tandon. And his research combines choice modeling techniques and big data analysis to explore travelers' behavior informatics for urban and transportation planning. And his dissertation develops an agent-based mixed logit approach to estimate deterministic coefficients from ubiquitous data sets within an acceptable computational cost. And we're also joined by Dr. Joseph Chow, Associate Professor in NYU's Department of Civil and Urban Engineering, and the Deputy Director of C2 Smart. So quick notes before we get going. We will be recording this session and uploading it to our YouTube channel. And we encourage everybody to ask questions today. And you can do so by pressing the Q&A button at the bottom of your Zoom window. And then we will read out your questions at the end of the presentation. And with that, I will hand things over to our presenters to get us started.
Okay. Can everyone see my screen?
Yep.
Okay, thanks. Hi, everyone. Thanks for attending to the C2 Smart webinar. My name is Xu Yuan. I'm a PhD student of Professor Chow. So today, my topic of presentation is New York State Behavioral Equity Decision Support Tool with Replica's synthetic population data. First, I will briefly introduce the background of this project. There's indeed a growing concern on transportation equity issues, not only from the government documents like the Transportation Equity Act for the new century, but also from a series of news and projects focusing on transit access and fare system towards disadvantaged groups. Transportation behavior equity describes a normative condition in which no person or no group is disadvantaged by a lack of access to transportation service they need lead to a colorful life. However, at the state scale, it's not that easy to consider equity issues. One of the enduring challenges in statewide transportation planning is that consistent population travel data remains scarce, particularly for underserved and rural communities. Planning models are often only estimated using survey data collected by the metropolitan planning organizations for the urban areas, not for rural communities, which are at risk of increasing inequities. So we initiate a one-year project that's focusing on developing a New York statewide behavioral equity decision support tool. In the first 3 months, we ingested vendors' data to our own data platform and checked their data quality. In the next 6 months, we developed a state-of-the-art multi-choice model, which can estimate travelers' preference on trip mode choice along each census block group level OD pair. We call this a GLAM logit model. And in the final 3 months, we integrate the taste coefficients from GLAM logit into a service region optimization tool, which forms our decision support tool. Given a new mobility service and an operating strategy like maximizing total revenue or minimizing transportation inequity, we solved the optimization problem to propose the ideal service regions as well as its potential impacts on transportation inequity. Replica is our main collaborator. Replica provides synthetic population data in a very large scale. And I also have a half-year internship there for this project. They have a sound methodology and diverse prototypes to show how synthetic population data can help to support a better decision-making. In this project, we use their New York State synthetic population products as our basic data. So the aim of this research is to first ingest replicas synthetic data and check the data quality at the New York State and the New York City level. Second, develop a state-of-the-art model that deterministically fits the mode choice taste coefficients for trips along each census block group OD pair. And finally, formulate a choice-based service region optimization tool to support the decision-making of statewide new mobility surveys with equity concerns. Here is a general framework of our project. The initial inputs are Replica synthetic dataset, and the final output is a behavioral active decisions for tool. In the middle of them are a series of works to reach our objective, including the data ingestion, estimation of taste coefficients, and formulation of optimization problems. In the rest of today's presentation, I will introduce them one by one. And okay, first, let me talk about the data ingestion and validation. This section includes the data validation and the description on the statewide scale and some trip details visualization for typical cities in New York State. Also, we generate a data quality report, including all of the results in this section. The data sets provided by Replica company include a population table and a trip table for the New York State in the fall 2019 season from the September to November. The population table contains records for each synthetic person by Replica. The information in each record includes a set of attributes describing the person's social demographics, like the gender, age, income level, employment status, and also contains their work, home, and school locations. The trip table contains each trip produced by Replica for a given synthetic person. Fields of each trip record includes its origin, destination, travel mode, travel time, and travel distance. Records from the trip table can be directly joined to the records in the population table using the unique person ID and unique household ID. For public transit trips, the access time, egress time, in-vehicle time, and number of transfers can be further inferred since Replica's data provide the entire routes of each trip. And their trip data mainly includes 6 modes, namely driving, public transit, on-demand auto, biking, walking, and carpool. With an access to the Google Cloud platform, we can visit their database through BigQuery. And based on the block group ID, which is a long string combining zip code of the state, county, census tract, and block group, we can pick out the region we are interested in, as well as aggregate the individual level trip data to block group level trip OD pairs. The regional data quality report generated through Replica's own data pipeline used the census data, longitudinal employer household dynamics data, census transportation planning products data to check the accuracy of synthetic demographic characteristics and their trip details. The report includes a quality check of resident population by census tract, by household income, age, gender, employment, vehicles, school environments, and trip and origin and destination flows. In general, the demographic attributes of the synthetic population are 95% accurate compared with the census data. And the trip mode share by census tract is about 90% accurate compared with the CTP data. The full quality report can be accessed through this link. As for some basic statistics of the data, the total residents in New York State is about 90.4 million. Total trips in New York State is about 53.3 million. and the trip rate is about 2.74 trips per person per day. We separate the total population into 4 segments, namely the low-income population, not low-income population, senior population, and student population. As for their mode share on weekday, senior population has the highest proportion of driving for about 60%. Low-income population has the highest proportion of public transit for about 20%. Students have the highest proportion of walking and carpool for about 29 and 27% respectively. Here, we can see the distribution of their trips in space. We can find the trip length of senior and student population is relatively shorter than low-income population and not low-income population, which is also aligned with our intuition. And as for the New York City, the total residents are about 8.4 million, total trips are 23.9 million, and the trip rate is about 2.85 trips per person per day, slightly higher than the trip rate in New York State. As for the mode share, we can see public transit and walking count for a larger proportion, for about 33% and 21% respectively. Also, we plot the mode share per trip OD pair in space. We can see trips related to Manhattan obviously have a higher proportion of public transit. And for those small trips, walking is the first choice. So till now, Replica's synthetic population data shows great consistency with the traditional survey data and our empirical knowledge, which we believe it is helpful in the next modeling step. And for more details of the data description, we refer interested audience to our project report or Replica's website. And with the statewide synthetic population and their trips, the next step is to build a statewide mode choice model to estimate travelers' mode preference. This is the most important part in our project, since the calibrated taste coefficients directly reflects the utility of using different modes in different zones by different population segments, which are good reference and basic reference for the equity-based transportation planning. And these coefficients later will be directly integrated into our decision support tool. Previously, we have a published paper about the similar methodology, and there is also a working paper for this case study. Here comes our second step, the statewide mode choice model. However, the existing discrete choice models are not that suitable for a large-scale dataset. The first challenge is that traditional discrete choice models can only capture individual heterogeneity with assumption of distribution. For example, discrete choice models assumes a specific distribution of coefficients, like the Gaussian distributed coefficients in mixed logit. We can only get a set of mean values and covariance metrics for the estimated coefficients. But the spatial information behind that are overlooked. This is not good for equity concerns. And the large dataset might not be suitable for statistical assumption. On the one side, these datasets have large sample size, which makes it no longer necessary to transfer from a sample to the total population. And on the other side, these datasets show an empirical distribution. In that case, the assumption of parametric distribution like normal distribution may cause some model misspecifications. The second challenge is that discrete choice models are stochastic estimation approaches. They generate nonlinear and non-convex demand functions. The consequence is that to get a single realization from the model, we have to use sampling approach. And sometimes it's complicated if we allow dependencies among these coefficients. The complex expressions restrict further integration into optimization models, such as the service reason assortment problem later formulated in our decision support tool. So for our project, we need an estimation approach that captures taste heterogeneity without any distribution assumptions. And the coefficients should be deterministically estimated to be further integrated into coefficients optimization models. Well, there are some existing approaches to deal with these challenges. First, mixed logit with a conditional taste density is a classic model dealing with individual taste coefficients. The taste density of each sampled individual is derived conditionally on the choice observations for that individual and the population distribution estimated by a standard mixed logit. But this kind of model still assumes parametric distribution of individual tests. And secondly, the individual parameter logit replace the maximum log likelihood estimation with evolutionary and gradient-based algorithm in order to search for individual level parameters that have the best fit to the observed data. Well, this approach often is computationally demanding and very sensitive to the initial candidate pool. Different searching algorithms will result in different different results. So finally, we choose inverse optimization approach, in which the missing coefficients are imputed from observed choice by assuming individuals are making decisions to maximize their overall utility. And this is theoretically in line with discrete choice models. Coefficients per individual or per agent are estimated deterministically by solving a number of quadratic programming problems, which is much more efficient to solve. Here comes our model form. We call this group-level agent-based mixed logit, or GLAM logit in brief. GLAM logit provides non-parametric estimation of K-model taste heterogeneity for each agent. It consists of three parts. First is the agent-specific coefficients, theta I, and the means of coefficients for cluster K. We minimize the L2 norm distance between the agent level coefficients and the K cluster means. Second, the constraints of inverted market share. Since in our model, a group of choice are presented as an agent instead of a single choice observation, the binary choice variables are aggregated into the market share, and we use the link between alternative utility and the inverted market share to ensure the estimated coefficients fit into the observed data. Third, the coefficient boundary and cluster indicator. A limitation in previous models is that it's hard to set a sign of some coefficients. Like we want to make sure the coefficients of travel time to be negative. Otherwise, it will be counterintuitive. Since the GLAM logit is actually solving a series of programming problems, we can set lower bounds or upper bounds for some coefficients and introduce the cluster indicator to ensure each agent belongs to only one of the clusters. Here we compare our model with mixed logit model and individual parameter logit model. The significance of our model can be summarized into 3 points. First, the taste heterogeneity is captured through a bottom-up logic. For example, a unique set of coefficients is estimated for each agent instead of first assuming a parametric distribution or searching taste candidates. This allows GLAM logic to capture taste heterogeneity with great flexibility and capable of identifying the taste clusters. Second, our approach splits a large-scale optimization problem into much smaller inverse optimization problems that can be solved in parallel. By doing this, we can avoid generating highly diagnosed sparse metrics that might use up CPU memories when the sample size is large. And third, since each agent's representative utility function is fully specified, GLAM logic can be directly integrated into system design optimization models as demand estimates, instead of dealing with simulation-based approaches needed for mixed logic and some non-parametric logic models. The proposed algorithm looks like this. We start from k fixed point priors, one for each taste cluster, and set all of the coefficients to 0. In each iteration, we run inverse optimization for each agent, then get all of the agent's coefficients and conduct k-means clustering algorithm to identify k-taste clusters. And then update the fixed point priors with methods of successive average. At the end of each iteration, we'll check the percentage change of the coefficients. If the change is within a threshold, we finish the algorithm and output the coefficients. And if not, we step into the next iteration. Here is an illustrative sample to show how GLAM logic works. The upper table shows our sample data, which includes 8 agents. Each agent represents a group of trips along a triple OD pair. In this example, we only consider 2 modes, namely the taxi and transit. And for attributes, we consider travel time, travel cost, and transit-specific constant. We set the number of cluster to 3, and the estimated market share from GLAM logic is quite similar to the sample data. In addition, there are 3 taste clusters identified. Cluster 1 has a negative coefficient of travel time, indicating a preference for shorter travel time. Cluster 2 has a negative coefficient of travel cost, indicating a preference for lower monetary cost. And cluster 3 have positive coefficients, indicating an irregular preference for longer travel time and longer and higher cost. This is a trick, since in agent 8, we set the taxi time and fare to a very high value, and at the same time set the taxi share to be 90%. So we add a fake sample. And to this end, the advantage of GLAM logic is that it can pick out bad samples by identifying them as a separate cluster. Okay, next we apply GLAM logic to New York State choice modeling. We grouped trips conducted by each population segment and along each block group OD pair as an agent, resulting in 120,000 agents in New York State. 6 modes are considered, including driving, public transit, on-demand auto, biking, walking, and carpool, which is the same as Replica data. 12 mode attributes are considered, including auto travel time, transit access time, transit egress time, transit in-vehicle time, number of transfers, non-vehicle travel time, trip cost, and 5 mode-specific constants. We compared the results of GLAM logic model with mixed logic, conditional mixed logic, and individual parameter logit. The results show great consistency in size. For example, the time-related coefficients have negative signs, and the constant for on-demand auto and biking also have negative signs since their mode share is quite low. If we set all of the coefficients to be normally distributed, mixed logit and conditional mixed logits cannot converge, which is one of the drawbacks of the parametric estimation. So here, sum of the standard deviation of the coefficients equals to 0. The individual parameter logit and GLAM logit took longer time to converge. The individual parameter logit took about 1.3 hours, and our GLAM logit took about 2.1 hours. But they also result in higher performance in terms of log likelihood value. Here is the empirical distribution of taste coefficients of the two clusters. These coefficients are revealed to be neither Gaussian or any other parametric distribution. Cluster 1 counts for about 75% of the agents, in which constant of transit, on-demand auto, and walking are large negative values. This cluster probably refers to longer trips in rural areas. And cluster 2 accounts for 25% of the agents, in which the value of time, the ratio between coefficients of auto travel time and trip cost, it is higher, and the standard deviation of mode-specific constants is larger. So this cluster probably refers to trips in urban areas with diverse mobility options. Also, when we compare the in-sample and out-of-sample performance, here in-sample refers to the dataset we use for training, and out-of-sample refers to the data we use to test data, which is another year of 2021 from Replica's dataset. The GLAM logit results in higher in-sample accuracy due to its agent-specific estimation. And the impact of overfitting is not that large because we are modeling the group-level mode share instead of individual choice. You can see it drops from the 96% to the 89%. It only drops about 7%. When we check the value of time of different population segments, the average value of time in New York City is generally higher than that in New York State. Not low-income population have the highest value of time in all of the segments, for about $13 per hour in New York State and $28 per hour in New York City. And low-income population and senior population have relatively lower value of time. And we visualize the value of time in space. We can see many trip agents in rural areas which are not available in previous models have been shown. So the synthetic population data gave us a chance to bring them back and build an estimable model considering these underserved areas. In New York State, the value of time in New York City, Albany, Buffalo, Syracuse, Rochester, and Osaka is obviously higher than in other areas. Among these cities, New York City has the highest value of time, which is definitely. And in the New York City, trips related to Manhattan and trips pointing to the JFK airport have relatively larger value of time, while trips in the Staten Island have lower value of time. Such a spatial distribution is only available with our agent-specific estimation in the GLAM logit. Also, for the transit-specific constants, a higher value indicates a greater preference of public transit. We can see some clear subway lines from Queens and Brooklyn to Manhattan. And the walking specific constant indicating preference of walking is higher in agents related to shorter trips, especially in Manhattan. So till now, we have validated our model results not only with performance metrics, but also by checking the spatial distribution of value of time and mode specific constants. This is important for transportation equity analysis, considering the user preference, and will be directly used as a proxy of equity metrics in our final step, the decision support tool. Well, the final step is to combine synthetic population data and estimated model choice coefficients to develop a choice-based decision support tool. We have a conference paper for IEE ITSC and also a working paper for the overall methodology. Yeah, the basic logic of our decision support tool is to formulate a choice-based service region optimization problem. Given a new mobility service, we should know its service time and trip fare on each OD pair, and with a specific operating goal, such as maximizing the total revenue, maximizing the total welfare, or minimizing the transportation inequity. Our tool proposed an optimal service region and fleet size by solving an optimization problem. Also, we calculate the operating and equity metrics regarding optimal solution to check the potential impacts on revenue collection and transportation equity. Traditionally, service region optimization or service region assortment is a complicated mixed integer programming problem, since the demand estimation of mode K is nonlinear. According to mixed logit models, the demand is related to the choice probability, and the choice probability is an integration of case density and alternative attributes. This is not a closed form, but in GLAM logic, the agent level coefficients are deterministically estimated, so we can result in a closed form of mode demand, which means if we assume the total travel demand remains the same or increased to a given number, the demand of each mode on each OD pair can be calculated in advance. And the service region assortment problem becomes a linear or quadratic programming problem that has efficient algorithm to solve on a large scale. Parameters in our optimization model consist of three parts. First, the trip attributes observed from synthetic population data, which is a product of our first step. And second, the deterministic taste coefficients estimated by the GLAM logit, which is the product of the previous, the second section. And third, variables defining the budget level and performance of new mobility service. For the budget level, we consider the maximum number of operating zones. We use county as the spatial units. Also, we consider the maximum fleet size in total, measured as vehicles per day, the maximum and minimum fleet size in each operating zone, and the maximum distance a vehicle can serve per day and the maximum number of trips a vehicle can serve per day. The decision variables include yi that indicates whether county I is selected as the service region, XUW that indicates whether the OD pair from block group U to W is served, and FUW that indicates the fleet size on the OD pair. We include three objectives in the decision support tool. The first is maximizing the total revenue, which is the sum product of trip fare and demand of the service on each OD pair. The second is maximizing the total change of welfare. The welfare is measured as the log sum of mode utilities in our GLAM logit model. It is also called the consumer surplus. And the third objective is minimizing the transportation inequity. Here, inequity is defined as the welfare disparity between non-disadvantaged communities and disadvantaged communities. The disadvantaged communities are published on the state government website according to household annual income and population density. And we have a set of choice constraints, ensuring that the total fleet size and number of operating zones are within the budget. For the single service region optimization, all of the objective functions and constraints are linear. So the problem can be solved as a linear programming problem. Well, if we want to consider the service region of two new mobility services, the problem then becomes a quadratic programming problem, which is a bit different from the current formulation. We refer interest audience to our final report. And in a prototype of our tool, we consider two hypothetical mobility services entering into the market. But users can also define their own service as long as they have the travel time and cost function. Service A is a personalized ride-hailing service with a trip fare that is 1.2 times of on-demand auto and a trip duration that is the same as driving. Service B is a carpool service with a trip fare that is half of the on-demand auto, but a trip duration that equals to on-demand auto plus 5 to 10 minutes waiting time. We set 3 budget levels, namely 5 zones with 2,000 vehicles, 10 zones with 5,000 vehicles, and 10 zones with 10,000 vehicles. For equity metrics, we calculate the consumer surplus as the basic indicator, and based on this, the average, the variation, and the pairwise difference of consumer surplus are calculated to measure transportation inequity. Here is the optimization results of the single service scenario, which we assume only service A entering the market. Entries in blood font here indicate the extreme values found for each metric across the 3 different objectives, which proves that our model indeed optimized the objective function. The percentage change of some metrics is relatively small, though most of them have expected size. This is because the new mobility surveys can only impact a very small part of the total trips, for about 2.5 in the whole state. Maybe we need to increase the budget level later. And in the optimization results of the multi-service scenario, considering both service A and service B, the total revenue and VMT per vehicle and number of served OD pairs are also calculated separately for service A and service B. Here are some findings by comparing the aforementioned different objectives and scenarios. First, service A has a smaller VMT per vehicle, larger total revenue, and more OD pairs to serve compared with service B. We found maximizing total revenue and maximizing total welfare will actually increase transportation inequity by up to 1.2% and 0.7% respectively. Well, minimizing welfare disparity helps to decrease transportation inequities by up to 9%. So it is at the cost of losing nearly half of the total revenue. If we click the links here, we can get a visualization of the optimal service region by our predicted by our tool. Here, the blue links denotes OD pairs with service A. The red links denotes OD pairs with service B, and the green links denotes OD pairs with both service A and service B. And we can see different objectives will result in different operating strategies. For example, here, if we want to maximize the total revenue, we will choose to operate in Manhattan. And if we want to choose to minimize the transportation inequity, we will focus on other operating zones. Okay, finally, to sum up this research, this project checks the quality of Replica's datasets, built a GLAM logic model for statewide trip mode choice, and develops a service region optimization tool for new mobility service in the future with equity concerns. Here is our complete methodology framework. And here are some common questions about our project. I'd like to mention them before the Q&A section. And first, why estimating coefficients at the agent level? This is because we want to capture the heterogeneity at a statewide scale instead of only statistically by assumption of parametric distribution. And in our experiments, the results have a higher accuracy for the optimization in later decision support tools. And second, about assumptions in the service region assortment model. Actually, we assume two hypothetical mobility surveys. We use the relative trip fare and trip duration for simplicity, but users can define their own travel cost and travel time functions if necessary. So in the future, maybe more research should be conducted to define the cost and performance function that are more close to reality. And third, about the computation time, risk of overfitting, and model transferability. The computation time is a bit longer than mixed logit, but it's still acceptable. It's about 2.5 hours for a statewide model. But the optimization is very quick once the model has been estimated. Each scenario only takes about 5 to 8 minutes to get the optimal sub-region. And the impacts of overfitting issues are limited, partly because we use group level market share instead of individual level choice observations. And also the ubiquitous datasets Replica provides us contains nearly the total population, which also helps to reduce the risk of overfitting. And finally, any deliverables of this project, we have estimated mode choice coefficients, codes for GLAM logic and decision support tool, and final project reports available. And the audience can access them through these links. Okay, that's all of my part today. Thank you for listening and welcome for questions and suggestions.
Great, yes, thank you. And as a reminder, we welcome all questions. So if you have one, you can enter it by pressing the Q&A button, which is at the bottom of the Zoom window.
Let me check. Okay.
We don't have any at the moment.
Yeah, I don't see any questions unanswered here.
We don't have any yet. So if anybody has one, feel free to add it. We can give it a little bit. Otherwise, we can wrap it up. Feel free, if you're adding one, you can keep going. But otherwise, thank you everybody for joining, and to our presenter for today's webinar. A recording will be available on the C2 Smart Center's YouTube channel and website. And as always, this webinar was brought to you by C2 Smart and the US DOT's University Transportation Center program.